Okay, thank you. So I'm Mario Baldi, and I'm going to tell you about programming environment for P4 programmable switches, which is called daPIPE, Data Plane Incremental Programming Environment. I'm going to first of all give you the context in which this came up, and then I show its application on a use case, which is the last use case that Alan just presented, so we know already the use case. By the way, one difference with respect to what you saw before right now is that I'm going to use P414 rather than P416, and you will see in a second why. First of all, to figure out how this works. So to set the context, what are the possible deployment options that we have for programmable switches? So most often, I have the impression when we think of P4 programmable switches, we think of a sort of white box deployment mode where we have a programmable switch with a programmable chip, and the end user writes or uses available P4 code and an available control plane, either like an OS or a controller, a remote controller that controls multiple switches. And so this gives a lot of flexibility because we can change the pipeline, we can have the features we want, but it also provides a significant disruption with respect to what most users of network devices are accustomed to do. So another possibility is to offer programmable switches as turnkey boxes. And this is, for example, the route that Cisco has chosen, likewise other vendors have chosen, where we offer a device that's based on a programmable switch, but we offer it with already a P4 program on it. Possibly we give the options to choose among a set of different profiles or different programs that the customer can choose among, and we offer a network operating system on top that controls the program. And this way, the switch is developed as usual, as the switches that customers were accustomed to that were not programmable, with the familiar features and interfaces. In our case, for example, for what data center switches are concerned, they will come with an XOS, with the typical NXOS interface and features. Now, this is good on the one hand, because, again, it's very similar to what customers are accustomed. It's the same. In addition, the fact that we have a programmable switch gives us the advantage that we can optimize resources. The switch is going to be future-proof. And, the usual advantages, we have more feature agility. We can more easily offer new features. And in addition, for example, in our boxes, we can provide INT, which is a novelty right now, available only on the Tofino switch. But on the other hand, if we go this way, there's not much flexibility. The end user, the customer, our customer, cannot really take advantage of the programmability of the switch to develop new features or to support new protocols. So the idea through which we came to daPIPE is to provide the option of a hybrid deployment. So our customers can get a switch that has already a P4 program and an operating system on top, but they can develop their own features by themselves. They can add their own features by themselves or by a third party. They can get custom features developed. And of course, then at that point, they also have to develop some sort of a control application that will run, for example, on the box, on top of the operating system, or it can run remotely. And it will control only the new features through, for example, P4 runtime interface or the daPIPE offered by Barefoot for their switch. So in this case, we have a best-of-breed solution where, on the one hand, customers can start deploying the device as usual. They might start taking advantage of the INT feature, and then they can add new functionalities. And when they do that, they do it with the minimum development effort, because they can focus, as Alan was saying before, in his case, they can focus only on that particular feature they are interested in. They don't have to worry about forwarding of IP packets or Ethernet frames. That's already taken care by the vendor.p4 part of the p4 program. And so this way, customers can take advantage of programmability in the platform, but with minimum disruption with respect to what we were doing before, and also with minimum risk, in the sense that the new code that they are going to use, the code that is newly developed and maybe not so fully tested like the one that the switch is coming with, is only handling a minimum of functionalities. So daPIPE is a development environment to support this deployment model. And this deployment model has a number of challenges, because in the moment in which we allow customers to add their code, here we have to make sure that that code is not going to go and break what works. So we want to make sure that when the customer P4 code is being added, it's not going to affect the existing P4 code, which is well tested and well proven. We want to make sure that customers don't need to know anything about that vendor P4 code that was on the switch. On the one hand, it's a complex piece of code, and it would be complex. It would be lengthy and time-consuming and requiring lots of effort to go and learn about it. On the other hand, vendors might not want to share that piece of code with their customers. We have, of course, issues with resource availability. Right now, existing chips don't have a huge amount of resources. As we heard yesterday, for example, Barefoot is already ready to release chips that have more resources. But for the time being, we are quite limited with resources. And in general, that's something we'll have to take into account, even when we'll have chips with more resources, because we will want probably to fit more features. And then, very important, there is no independence between control plane and data plane, as we know. So in the moment in which the customer is going to go and modify the data plane, we need to make sure that those modifications are not going to affect the operating system that is shipped with the box. Otherwise, those additional features or that additional P4 code might compromise the operation of the whole box, because the operating system is not going to be able to control the box properly anymore. So we need explicit support to do something like this. And we call something like this incremental programming, because we don't want just to write a P4 program, standalone P4 program. We want to write a P4 program that incrementally is added to an existing P4 program. And we need support for that. And the way we address those challenges that were listed before is by basically identifying constraints that we have to put on the new code. So yes, we can write new code, additional code, but not anything. We will not allow customers to write any kind of code, make any kind of modification. We will constrain what kind of modifications can be done. And we will impose those constraints on the code. We will do this through the development environment that the customer will be able to use. So what is the workflow at this point? The idea is the customer will write their additional code. And again, they will just focus on their functionality. They don't have to worry about all the basic functionalities that are already in the vendor code. And then their code will, first of all, go through some constraint checking to make sure that it satisfies constraints that ensure that those challenges are in check. And then their code will be merged and compiled. I'm sorry, the microphone. Merged and compiled with the vendor code to generate a binary that's then loaded on the switch. On the other end, of course, the compilation will generate also all the required libraries represented there by that object daPIPE.o. And this will be used when the customer will write the control part, the control program for their features. And that control program will be written in whatever language they prefer. They will maybe take advantage of some APIs that the operating system will provide to access data structures and information related to the standard functionalities that the system is offering. So, for example, if the system, the network operating system is running routing protocols, it's collecting routing information, it has a routing database, maybe the control code needs to go and take a look at information in that routing database to control the function. It's just as an example, right? And then that control code will be compiled, obviously using also the libraries that were generated by the compilation and executed in this example directly on the switch on the operating system. But as I said, it could also be executed remotely. So the control can also be remote. And the bottom part is what is being done by the development environment. Verify constraints, merge the code, and compile it, and load it on the switch. So as I said, we call this concept of writing P4 code in addition to an existing P4 code incremental programming, and because we are programming on the data plane incremental programming environment, and this is the acronym of the environment we have. So this environment is basically supporting developers in writing their additional code, their incremental code, and also it tries to streamline their tasks. So there to the right you have a screenshot of the current prototype we have of this environment. And the idea is, in fact, the environment is trying to help the developer go through the various stages of adding this code. So it allows them to add headers, new parsers, new tables and actions, and then define the control flow according to which those tables will be applied. And then it allows to compile the new code, and again, this new code will be compiled together with the pre-existing code and uploaded on the switch. The environment is actually composed of two different components. A graphical user interface just to help the user write code, and also limiting the kind of actions that the user can do, and providing a little bit of insight into the pre-existing code already uploaded on the switch, but in a guided way. So first of all, it doesn't provide the full visibility of the code. It provides visibility only on certain information, namely the headers, the metadata available, some of the actions available that can be reused. And then we have a build environment, which is optionally separate. They can be run in the same environment, the graphical user interface and the build environment, or they can be physically separate. And the idea is the user uses the graphical user interface to write its code, and then when it hits the button compile, the code is shipped to the build environment that is merging the code with the vendor code and uploading it on the switch. And uploading it on the switch, it also updates the API information for the new code, and the control program that the user will have written separately will use that API to control the new code. And right now we have implemented this for our Nexus switch 34180YC, which is based on the Barefoot Tofino chip. But what we have done is pretty generic. I mean, it can be applied also to other platforms. But right now, it works on that platform, and well, a little bit of commercial here, just a small commercial break, but not really. I mean, just to give you an idea of the capability of the switch we are shipping is the one at the top. It has 48 10 gig interface, 1025 gig interface, and 6 100 gig interfaces. And it's based obviously on one of the Tofino 1 chips. We have an upcoming model based on another Tofino chip that has a 6.4 terabit per second switching capacity, which is going to be called Nexus 3464C, and that one has 64 100 gig interfaces. Well, both support INT, which, again, is, as we heard in the past days, is one of the features that are offered on the Tofino chip, well, on any programmable chip, but in particular on Tofino, and we support it in an XOS. So this is how we got to daPIPE, and I'll give you an overview of how daPIPE can be used with a use case, which is, in fact, the use case we were talking about before. So I'm going to skip a couple of slides that were describing the use case. Well, Alan didn't say this use case. I think you didn't say this use case is published on the internet. That's why I use it. It's totally public. You can find it at that URL. And it was published by Fox. So, okay, we saw what is the idea. Just to dig a little bit more into how this problem, this use case can be solved, the idea, I mean, Alan already said, is we go and look at the timestamps. And also, I think, well, yeah, you sort of mentioned, but anyway, the idea is, and this example is on the website, on the GitHub page I was showing you before. The idea is if you have, for example, packets that come in with a certain multicast address, for example, 239.1.1.1, and the RTP timestamp is within a certain range, then what you want to do, you want to basically change the destination address. So what the P4 code has to do, I'm telling you this because now we go and write the P4 code into the environment. So just to give you an idea of what we are trying to do, we are trying to look at the RTP timestamp, look at the IP destination address, and then if the RTP timestamp is within a certain range and the address has a certain value, then we change the destination address. And here, by the way, you can see the value of incremental programming. We can really focus just on this. Then we don't have to worry about, okay, now how do we forward that packet that has that particular destination address? That's going to be done by the rest of the code, by the rest of the vendor.p4 code. And as Alan was mentioning, we also have all the components that are related to IGMP, subscribing the groups, and so on. Well, that's handled, that's supported. Of course, IGMP is supported, but supported by the operating system that's running on the box. So in addressing this use case, we don't have to worry about those common functionalities. Those are already in the operating system and in the vendor code. Okay, we focus just on doing exactly this. And you know, in the presentation before, took away a bit of the of the message here, but or gave the message before. But the beauty is you write very little code. I mean, Alan already showed it before, but you'll see it also now. It's really very few lines of code to solve this use case. If you would have to solve it completely, you would have to write also all the code to forward multicast packets to, you would need to write all the parsers for Ethernet, for IP, and so on and so forth. Instead, in this case, all we need to do is to define additional custom headers, like in this case, the RTP header, because a typical switch is not going to go and look into RTP. So the vendor.p4 program doesn't have an RTP parser. How do we know it doesn't have an RTP parser? Because, as I said, we don't have visibility into the vendor code. Well, the environment is going to give us a little bit of visibility. As you will see in a second, it will show us the existing parsers. It will show us the existing metadata being extracted by those parsers. So we can see what we have. We can see that the IP address, obviously, is already extracted by the vendor code. We don't need to write a parser for that. And we can see what is the name of the metadata that contains the destination addresses. Like this, we can reuse it in our custom code. Okay, so that's what the environment is, how the environment is helping us into going through these various stages. It's first of all, first bullet point showing us what we can use already. And then we can go define new headers, we can define new parsers. And when we define new parsers, we need to be able to specify how that parser, when that parser is going to be executed. And we will see daPIPE as the concept of a hook in the parsing tree that can be used to specify where the new parser goes and is attached to the parsing tree. And then we can define custom tables and actions, specify the control flow, and at that point we are ready to compile and put on the chip. And then, of course, we would need to go and write the control plane part of the story, which I'm not showing here. Again, when you start daPIPE, you get this window. It's, just to be clear, this is not a Cisco product. It is an experimental product. It's usable, but it's not supported by Cisco. That's what that disclaimer is saying up there. So first of all, if we want to add new header, like we want to do in this case, we can go and see existing headers. There you see the GUI is showing, I've selected there the IP header, and it shows me the existing fields that are parsed from the IP header and how they are called all the way there to the end, to the right. And then we can go and add our new header. And there I started adding the RTP header. I'm not going to go into the various details, but basically, I mean, it's just a graphical interface that enables me to type in the various fields of the RTP header. In the previous version, we just had an editable field with, one would write P4 code. It's equivalent. It's nothing fancy, but just to guide the developer. And the other thing is, besides guiding the developer, is also constraining the developer. The developer cannot go and change the IPv4 header definition or any other existing header definition. Then we want to add a parser. And in adding a parser, what the environment does, it shows us the existing parsers, and we can go there. And we can see for any parser, the environment is giving us possible hook points. So I don't know, let's say if we wanted to add a new version of IP, then we would go to Ethernet, and as a hook point, we would be showed ether type, and there we could define a new value in that field hook value. We could define a new value of ether type that identifies, for example, IPv7. In this case, we want to add RTP, and RTP has to be parsed whenever there is a UDP message. The system should attempt to parse RTP every time there's a UDP message. So we don't have a hook value, and also we don't have a hook point. We just say whenever you see UDP, as a default parser, run RTP. And the RTP parser does what's written in that box, extracts the RTP header, and then goes to the ingress. Okay. As you can see, that's, as I was mentioning before, P414. The reason why we use P414 is because our upcoming switch is supporting P414 right now. So that's why right now the environment is for P414. But obviously, as you can imagine, there's no reason why it should not be ported on P416. We haven't done it yet just because our switch currently supports P414. Okay, so then once you have added your new parser, it's going to be there among the parsers. So user-defined parsers can be viewed and can be modified, the others not, obviously. So again, the environment is putting some constraints on what the user can do. And then once we will compile, what will happen is that the new parser will be merged. The new code in general, in this particular case, the new parser will be merged with the existing code. And I mean, here you see an example of code that was pre-existing. The blue code is the new code, and then the environment generates some gluing code in red. Similarly, we can add actions, and I'm going to go a little faster here. You know, you can add your actions. There is an action that we use to rewrite the destination address, which is what we need. And again, the programmer will know that the destination address, the IPv4 destination address is IPv4.dstr because it can browse the existing metadata, as you see there on the top right side of the window. And then we can add tables, and here we need a table that has a key, which is the destination address and the timestamp meshed in a range. And as an action, we have our action up there. So all the code we need to write here is basically this, plus the header definition and the parser. Very little code to address this use case. And finally, what we need to do is to define where that action is going, where the table is going to go in the pipeline. And in this case, we place it, well, I'm sorry, there is a mistake up there. It's at the beginning of the ingress pipeline. I selected the wrong choice in the pop-down window. So we put this table at the beginning of the ingress pipeline. Like this, the packet comes in. If it's one of the packets that need to be translated, the destination address is translated, and then the packet is going to go through the stock pipeline where that multicast address will be handled properly. Okay, so at this point, we hit compile, and basically, I'm showing you these windows just to show that basically here we can specify on which of our switches this code has to end up. And we need to provide information about the remote IP address and username and password there are not for the switch, but they are for the, remember, the build environment that can be separate. In this case, I'm using remote compilation, so the build environment is remote. The build environment could also be local to the GUI. Depending on the deployment cases, you might want one or the other solution. But once we provide the environment with the graphic user interface with the information about the build environment and the switch, the code is sent to the build environment. The build environment generates the binary for the switch and the library and uploads them to the switch. And to conclude, what happens for the control plane? Well, the control plane, as we said, the user will have to write some custom applications that are running, in this example, on the switch itself. Otherwise, they can be remotely. And the operating system, on the one hand, will provide APIs to access the information that's available in the operating system, like the example I was giving you before, routing database. On the other hand, it will provide access only to the features that were added, so only to the tables specifically added by the customer P4 code. Okay, so just to conclude, as I said before, this is a solution that right now we are using with our Nexus switch, but it's not really specific of that switch. Can be used with any other platform or network operating system. And because I'm short of time, I'm gonna skip some of these considerations that I have already made before. Obviously, these will not address any possible use case. There will be use cases that cannot be addressed with this because you need to modify that vendor.p4. Well, they are not going to be supported in this case. But the benefit of this is you can use a box that has already a well-tested data plane and control plane, and you can add functionalities for those use cases in which you can just add them like that. And if you're interested in giving it a try, just get in touch with me, and I'm going to make it possible. You just need to be willing to deal with something that's very new, so not really perfect. Thank you. If you have any questions.